The next section 1.5, which is equivalence and countability. So you have seen the definition of function and the types of function, one-to-one function, on-to function, the bijective function. You may have seen these concepts. So let us recall a function. So suppose we have two sets, set x and set y. Then a rule map f from x to y will be a function if for each element of x there is unique image of y. So this can be also a function, but there should be only one output in the y, in the set y, right? So let us see what are the one-to-one function. Let's recall the definition of a one-to-one function. One-to-one function or one-to-one correspondence. So if f from a to b is a function, then f is called one-to-one function. F is called one-to-one, or simply we can write 1-1. If f of a1 is equal to f of a2 implies that a1 equal to a2 for a1 a2 in the domain A, right? It means what? A function will be one-to-one if, in which case, for the function, if images are same in the codomain, their pre-images, that means the proper elements from the domain, should be same, right? It simply meaning that the different elements from the domain maps to different elements in the codomain, right? So what happened to this case? In general, if this is the case, so what you can say about? So we have seen in this example f of x is y, f of x dash is y. So y is image of two elements from the domain. So can you say something about inverse image of y? So inverse image of y, so by the definition of inverse function, it will be the elements in the domain. Which elements? Those are having the output y or image y in the codomain. So in this example, what will be the inverse image of y? There will be two elements in the inverse image of y, x and x dash, because both the elements are mapping to same element y in the codomain, right? So a remark: if f is 1-1, and see what happens in general, this is a function. So what happened to the function if f is one-to-one function? So if f is 1-1, so in this case the different elements from the say domain will map to different elements in the codomain, right? So possibly there will be same number of elements in the domain and codomain, or domain and range, right? So in this case, if I want to find an inverse image of element y, so it will be a single element x. Why? Because here the function is a one-to-one function. So the remark is if f is 1 1 and b is equal to f of a1, then b is not equal to f of a2 for any element a2 from the domain, right? That means if f is one-to-one function, so every element in the domain will have unique image in y, and every element in y will have unique pre-image in x or domain, right? So let us see example. So this is the one-to-one function. It depends on whether the function is one-to-one or not. It depends many times. It depends on the domain of the function. For example, see, if I take a function fx, which is x square, and what if I choose the domain to be minus infinity to infinity, and what is the image? Image will be in 0 to infinity. So is it a one-to-one function? So definitely it is not one-to-one. And if I choose some other function, the same function with some different domain, and now I use the domain from 0 to infinity. So is it one-to-one? Yes, it is one-to-one. Why? Because in this case, f of 3 will have image 9 and f of minus 3 will also have image 9, and this is not the case in this domain, right? Because negative real numbers are not there. So there is unique number in the domain which is mapping to the unique number in codomain, right? So that is, therefore, a function f is 1 1 if f inverse of b contains a single element for each b in range of f. Right? Because in this case f is function from x to y and f is mapping like this, two elements from the domain mapping to same element in the codomain or range. It is a function. So can you guess something about f inverse? Whether it is function? It is not function, because the definition of function says that for every element of the domain there should be unique image in the codomain. But if we apply the definition of function on f inverse by the reverse way, for every element in the domain it should have unique image in the codomain, but it is not true, because in function f the mapping is like this way. So if we try to apply, or if we try to invert the definition of function, so f inverse will not be a function, because the element y of the domain of f inverse have two images in the codomain of f inverse, right? So f inverse will not be a function in such case. So in this case f inverse will be definitely a function, because f is one to one. Different elements of the domain are mapping to different elements in the codomain. So I don't need to worry if I am inverting the map or if I am trying to define f inverse from y to x, right? So the definition of function is also valid. Every element of the domain of f inverse has unique image in the codomain of f inverse, right? So let's see the definition of inverse function. If f from a to b is 1 1, then the function f inverse, it is called as inverse function of f, is defined as if f of a equal to b, then f inverse of b is equal to a, where b is in a range of f. So we can observe that the remark, the domain. So if f is one-to-one function, a is domain of function, b is codomain of function or a range of function. What about f inverse? F inverse will be a function from b to a. So what is the domain of f inverse? Domain of f inverse is b, and the b is what? Range of f. And range of f inverse, what is it? X, which is nothing but a, which is nothing but domain of function f. Right? So let us take example. Let fx is equal to x square. X lies between 0 and infinity. So then what will be f inverse of x? Now the function is 1 to 1 because it is defined from 0 to infinity. The negative part is not involved. The negative real numbers are not involved in the domain. So f inverse of x will be square root of x, and for this function the domain will be, f is function from 0 to infinity. What will be the output under x square? It will be 0 to infinity. And similarly, what will be f in the domain and range of f inverse? It will be 0 to infinity. Similarly, 0 to infinity. Similarly, the second example, if I take gx to be e raised to x, so it is exponential function. It is defined from minus infinity to infinity. So what can be the domain and range of this function? Exponential function, the output will be, it never gets 0, it never gets negative value, so it will be, it never gets 0, so open bracket is there, 0 to infinity. So if I want to define the g inverse, so what g inverse will be? The inverse function of exponential function will be logarithm of x. So what will be the domain of this function? So definitely it will be codomain of g, and the output of logarithmic function is minus infinity to plus infinity, and the domain is x to infinity, because logarithm is not defined for negative real numbers also and for 0 also. So next definition, 1-1 correspondence. One correspondence. So let us see definition. If f from a to b is a function, is a 1-1 function, then f is called a 1-1 correspondence. A 1-1 correspondence between A and B if there exists a 1-1 correspondence and equivalent set. If f is called 1-1 correspondence, and if there exists a 1-1 correspondence between sets A and B, then A and B are called equivalent sets. A and B are called equivalent set. So simply speaking, two sets are equivalent if there is a 1-to-1 correspondence between them. That means we can define, if we define a 1-to-1 map between the two sets A and B, then the two sets are equivalent. Remark. So can we define a 1-to-1 map between from a set to itself? Yes, definitely, because we can define an identity map from a set to itself. So remark, every set A is equivalent to itself. Number 2, if A and B are equivalent, then B and A are equivalent. If A is equivalent to B, then the set B is also equivalent to A. Right? Number 3, if A is equivalent to B and B is equivalent to C, A is equivalent to B, B is equivalent to C, then A is equivalent to C. So this equivalent sets is a like symmetric, transitive and reflexive, symmetric and transitive relation. That means it can be an equivalence relation. Next definition, infinite set. the set A is infinite if for each positive integer n A must contains a subset with precisely n elements. Right, that means what is an infinite set? If I want a subset of with 100 elements, so I should get there. If I want a subset with 1000 elements, so it should be there. If I want a subset with 1 lakh elements, so it should be there. So for any natural positive number n, I should get subset of A with this number of elements, right? So let we denote I to be the set of all positive integers that is I equal to the positive integers. Whether it is finite or infinite, definitely it is infinite, because with set of positive integer I can have any number of I can have a subset with any number of elements from this set, right? So definitely I is an infinite set. Similarly, we have set of integers, it is also a set, infinite set. We have set of rational numbers, it is also an infinite set. Or set of real numbers, it is also set of integers, set of natural numbers, set of rationals, set of real numbers are the examples of infinite sets. And then the next definition, finite set. A set that is not infinite is called finite. So the question is now, can we count the number of elements in every set? If set is finite, that means it is not infinite. Means the set is finite. So I can count number of elements, right? So if I have an infinite set, the question is, can I count the number of elements from this set? So from Z, can I count number of elements? There are infinite number of elements. From N, there are infinite number of elements. Can I count them? Q, set of rational numbers. R, set of real numbers are infinite sets. So can I count the number of elements? So the next definition is countable set or denumerable set. The definition is the set A is said to be countable or denumerable if set A is equivalent to set I of positive integers, right? That means that is a set is countable, A is countable if a map F, if the set A and I are equivalents, that means if from I to A is 1-1 correspondence. So simply speaking, it means what? This is set of positive integers and this is set A. It means the set is countable means I can give a counting scheme, or I can count the elements, or simply it is possible to give a counting scheme. This is first element, this is second element, this is third element, this is fourth element. So by this way the counting process will works there. So whether it works or not is the countable set. And the definition of uncountable set. So if the scheme of counting is not there, then the set will be uncountable. So the definition is an uncountable set is an infinite set which is not countable. So we have finite and infinite sets with respect to the number of elements and the cardinality of the set. What about finite elements? Are they countable? Yes. Countable means what? Whether the set is equivalent to set of integers. That means whether I can assign the counting scheme, to the elements of set. So if it is possible to assign a counting scheme, then the set is countable. So if I have a finite set, so definitely I can count the number of elements and it will be a finite number, right? So every finite set is countable. Remark, every finite set is countable. Let us take it as an example. Set A is 1, 2, 3, 4 up to n. So is a finite set, and definitely it is countable because I can assign a counting scheme. I can have a 1-to-1 correspondence between set A and set of positive integers. Remark, thus set A is countable if there is a 1-1 correspondence, 1-to-1 correspondence. There exists 1-to-1 correspondence between set of positive integers and A, and the elements of A are the images f of 1, f of 2, f of 3 and so on of the positive integers from I. That is, we can write the set A as f of 1, that means it is first element of set A, f of 2 second element of A, f of 3 and so on. That means the elements of set A can be counted. Right? Next example. A equal to Z, it is set of integers, is countable set. So how it is a countable set? So can we define some counting scheme? Can we define a counting scheme? So how we can define? So if we define, see what the function is defined. We define f from set of positive integers to z as f of n is n minus 1 by 2 if n is odd positive integer, and f of n equal to minus n by 2 if n is even positive integer. Now check whether we are getting all the elements from set Z. So the elements in this I are 1, 2, 3, 4, the positive integers, right? So if n equal to 1, so I will get 1 minus 1 to 0 upon 2. So I will get 0. If n is 3, so I will get 3 minus 1 is 2 by 2, which is 1. If n is 5, I will get 5 minus 1, 4 by 2, that means 2. So from this I will get 0, 1, 2, 3, that means 0 and the positive integers from this function. And if I come to this side for even values of n, so if n is 2, so it will be minus 1. If n is 4, it will be minus 2. If n is 6, it is minus 3. So this function will provide negative integers from z, and this function will give 0 and positive integers from z, right? So from this function f, I am getting all the elements of z or images of the elements of I, right? So clearly f is 1 correspondence. From I onto z. Therefore z is z or set of integers is countable. So observe one thing here. In z I have negative integers, then integer 0, then positive integers, right? So if I consider set of positive integers, so which is nothing but exactly similar to this set, right? So definitely set of positive integers is countable. 0 is a finite set of single element is also countable. Z minus set of negative integers will be definitely countable. Why? Because if we want z minus, so it is set of negative integers -1, -2, -3 and so on. So if I want to define a function from I to z, what I will define? F of n equal to -n, nothing else, right? So it is just a game of sign. So then z minus is also countable. So this z set of integer is nothing but union of countable set. So what you can say about the union of countable sets? Remark. If A and B are countable, then A union B is also countable. Right?